Hello everyone, and welcome to the 20th episode of the Space for Women show. Thank you for joining us. My name is Dr. Alisa Jihanadaji. I am a lecturer in space law and policy at Harvard University, former Planetary Protection Project Officer at the Committee on Space Research, COSPAR, and one of the hosts of the Space for Women show. Today, my co-host and fellow Space for Women show team member is Anna Christina. I am honored to welcome two fantastic experts in the field of astrobiology and astrosociology, respectively, Dr. Jen Blank and Dr. Gerhard Sonnert, to talk about life in the universe. First, we will have a presentation from Dr. Blank on what astrobiology is, and then Dr. Sonnert will explain to us what astrosociology is. I will then ask them a couple of questions before opening the floor to a live Q&A with our audience. Audience, please indicate your name and where you're connecting from in the chat, and feel free to post your question there during our live Q&A. We are live, we're ready to go, and so first, let me introduce you to Dr. Jen Blank. Dr. Blank is an astrobiologist at the NASA Ames Research Center in Silicon Valley and a researcher with the Blue Marble Space Institute of Science. She characterizes water and rock chemistry that supports microbial life and the mineral biosignatures the life deposits. Currently, Jen leads a field project that uses the Boston Dynamics Spot robots to look for life in lava tubes in Northern California. The goal is to develop and test science mission operations that may one day apply to the search for life in Martian caves. Jane has worked with the Mars Curiosity rover science team, planning science activities on Mars. Her formal training includes 2 bachelor's degrees in geology and English from Stanford, a master's degree in oceanography from the University of Washington, and a PhD in geochemistry from Caltech. Jen Blank is also a UNUSA Space for Women network mentor. So Jen, what is astrobiology?
Thank you, Alyssa, and thank you for the introduction. What is astrobiology? Well, for the next 10, 12 minutes, I'm going to, I hope, answer that and give you a few examples. So now I'm going to share my screen. What is astrobiology? Well, astrobiology can be almost whatever you want it to be. So it's a very broad field, but essentially it has to do with anything that addresses the question of what is life and where are the building blocks of life, where do the elements of life come from, and what feeds life, and where might we find life in the universe. So that's a pretty broad question. That means that when we go to conferences and go to talk with our colleagues, it can be very uncomfortable because it's very interdisciplinary. So I can be sitting next to somebody who's essentially a heliophysicist, or somebody who studies the burning of the sun, or I can be sitting next to somebody who studies metagenomics, looking for genetic signatures and trying to understand what gene markers they're finding in their samples. So it makes for a lot of interesting discussions, and you really have to sort of jump in and embrace the unknown, and I think it's a wonderful field. Anyway, briefly, what are NASA's main themes from the recent astrobiology strategy plan? I thought I'd share this because I want to emphasize here that we're trying to, in this episode, talk about astrobiology and astrosociology. And traditionally, NASA has not funded search for life, for intelligent life, rather, since the 1970s, when they made the conscientious decision to separate those two areas and really stop supporting SETI and instead focus on microbial life and sort of themes around that. So here are the themes. One is abiotic sources of organics. So in other words, where do we find biological and non-biological sources of organic material that could eventually give rise to the origin of life? What is the coevolution of life and the physical environment? How does Earth or how do other planets evolve to support life, and do they evolve together? We know now that the minerals of Earth in its early history were very simple, and today the mineralogy of Earth is very complicated. Did that require life to become so complex, or did it require plate tectonics, or both? Early life and increasing complexity. How do we go from a cell to us? we're working on these themes, as you can imagine. How do you make a habitable world? What does it take? Do we have habitable worlds in our solar system? Do we have habitable worlds elsewhere? What defines a habitable environment? Can we determine that? It's a lot easier to find things that support life than to find life itself, we found. And finally, how could we characterize macromolecules and the origin of life? So macromolecule can be anything from a tar or a very large organic molecule that we found in meteorites, but it could also be ribose or life organics or lipids. Okay, now I'm going to give you a couple examples, but first, the biggest question, of course, is what is life? Now, this is actually an ongoing debate. Is the corona-19 virus life? Well, by this definition, coined from a 1944 book by Erwin Schrödinger, yes, the Schrödinger of the Schrödinger equation in quantum mechanics, life requires reproduction and metabolism. In other words, it requires the ability to make a copy, and in fact, to evolve, it requires an ability to mutate or adapt and make a copy. And then it requires an ability to have a metabolism, i.e. use energy from outside itself to burn for fuel to keep itself going. Now, this is sort of a really basic definition of life, but I think it's actually a good one to start with. And then the heated discussion comes into the details, of course. But I'd recommend this book. It's pretty short, and it's written for a general audience, and I go back to it about every other year. Anyway, what is life? So this is the definition we traditionally work with. And how do we make life? Well, so far, we have not made life in the lab yet, unless you count artificial life as life, but we're not talking about that here. But the broad study of origin of life really dates back, a long time, but it first gained a lot of popular attention following this experiment by Miller in the early 1950s. So Miller was a graduate student at the University of Chicago with Professor Harold Urey. And at that time, they looked, people were looking at the atmosphere of Jupiter and saying, Jupiter is the biggest body in our solar system. Let's look at the gas chemistry. And maybe that's the gas chemistry that was around when life originated on Earth. And so that was a very reducing gas chemistry. In other words, it had lots of hydrogen-bearing gases like methane and ammonium and hydrogen, rather than what we see in our atmosphere today of oxygen and carbon dioxide. So they did this experiment and they sparked, you probably heard the making amino acids in a test tube. They used electric discharge to spark charge these gases, ionize the gases, and then they cycle through with boiling water in a condenser. Condenser is just cooling water to make things fall out of the air or the atmosphere. And lo and behold, they found amino acids. So this is a very sort of classical experiment, and many of you may have heard about it in school, elementary school. And you can see on the left, there's actually a picture of the original apparatus with the Tesla coils that they were used to spark the discharge. And here's the condenser and cold water circulating through. And here's the atmosphere in here, and you can see that brown gooky stuff. Anyway, turns out they made lots of amino acids. Not all 20 that we find in that we find necessary for life, or rather involved in life as we know it, but many of them. And in fact, what was that brown? The thing is that he made other stuff too. He didn't make life, but he was making a tarry substance. In fact, he stopped his experiment after a short time as he realized that the longer he let the experiment run, the more and more the small building blocks of life fell out of the experiment and stuck on the sides in this tarry, gooey substance. So that was a little bit of a complication, but it turned out that over the course of the next, 50, 60 years of Stanley Miller's career, he and others tried to reproduce this experiment in many different environments and found always they were able to make amino acids and some other compounds. So that was very, very inspirational. We thought, hey, we get the amino acids, we can make life. Well, as you can imagine, it's not quite so simple, but it led to thinking about where we could find life, where on Earth we'd find environments that support life. Well, Stanley Miller's experiments sort of correspond to this idea of lightning and volcanic plumes. And here's a picture on the upper left from, it is Jökull. It's a volcano under an eruption in Iceland that happened a few years ago under a glacier. And it's very common when you have large eruptions to have lightning. And you also have gases and reduced gases coming out of the volcanic chamber. So here's one environment on Earth where you could get that laboratory scenario of Stanley Miller. So that's one way to perhaps make amino acids. Another way to make simple building block compounds, not amino acids that we found, but could also give rise to the origin of life, include hydrothermal vents at the bottom of the ocean, where you find these small organic compounds and energy and heat to help drive life, or hot springs on the surface of the Earth. We think we found signs of the earliest life in the Pilbara in Western Australia, and the features in the rock record indicate that these could have been shallow hot springs on the surface of the Earth. But again, we don't have any proof of where life came from, and also life could have originated in more than one way, and eventually one type won out. We don't really know, but this gives us much to do in the field of astrobiology and origin of life science, and our discussions are on and research are ongoing. Another question or another area of astrobiology involves looking for the building blocks of life, or even for life beyond Earth. So did life on Earth come from outer space? And I spent some years of my career actually trying to simulate in the laboratory the creation of amino acids from comet Earth impacts. Now to do this, I used giant ballistic cannons in the national laboratories, but was able to generate amino acids and even peptides by harnessing the energy of shock. So that was sort of my 5 minutes of fame, but it was sort of unexpected at the time because of the huge energy release and temperatures that go up to thousands of degrees centigrade in these impact environments. And planetary scientists look beyond Earth. We do find evidence of amino acids in observing, and also evidence of sugar acids in meteorites that come to Earth, and amino acids there too. So these are all sources of building blocks. This is a picture of the comet 67P, and you may remember when Rosetta arrived here, and the Rosetta mission sent down the little refrigerator-sized philae to this comet, and it sniffed, it detected amino acids there. Now, of course, we're all anxiously waiting to see what happened to philae, because the gravity is so low on this body that it bounced a few times. And then we had to wait until the comet got close to the sun before the signal from philae came back. But anyways, it's a very exciting mission. Anyway, so we're excited though that we find these building blocks elsewhere beyond Earth. Having said that, there are still many questions to go, to take that we must understand before we go from building blocks or even protocells to life. So we've been able to make all of these sort of very simple compounds in the laboratory. We've been able to make compounds that are captured inside yeast cells or little protocells. We've been able to make different kinds of amino acids, or even synthetic molecules in the laboratory that are actually like RNA and DNA. But how do we make life? Well, I think that's going to happen in our lifetime, but so far we don't know. And so when you go to Origin of Life or astrobiology conferences, you actually find many talks on pre-life and many talks on characterizing life, and then there's this big gap. So this is an area open for all of you should you want to embrace astrobiology. Another area of study that really inspired the search for astrobiology, and actually in NASA's large investment in astrobiology, was the report of the life in the Allen Hills meteorite in 1996. And this was a Martian meteorite that was found in Antarctica. And here you see a picture of it on the left. And on the right, you see an enlargement, thousands of times actually, of what looks to be possibly microbial life. So this created a huge storm of interest first in the scientific community and then in the world, as to, and heated debate as to whether or not these things were life. Well, in the end, the consensus was that there was not enough evidence here, chemical or morphological or otherwise, to say this is life, and they could explain this texture through inorganic processes. So it was determined, rather, that this meteorite does not contain life as we know it, but still it made us look, gosh, this is cool, and there's so many places we could look for life, and astrobiology as a field within NASA was born. So how did life arise on Earth, another area? How do we go once we have life, and how do we come to now? Well, our best Earth is about 4.5 billion years old, And our rock record goes back to about 3.5, 3.6 billion years. But we don't have any real physical evidence of life. We have suggestive evidence of geochemical life and morphology. So this is, again, not absolute proof, but we think these are the best indicators. And this is an area in geology and geochemistry where there's a lot of interest also, looking for the oldest rocks on Earth in Australia, and essentially part of the old cratons that still exist on Earth, the oldest rocks in Australia and South Africa, and patches elsewhere, to try to understand the rock record to the best we can to see if we can learn more about how life arose on Earth. Another area is how are we related? Here's a summary of the tree of life that includes about 2.3 million species in this tree. Each of the sort of bars that parallel to the outer diameter of the circle represent about 500 species. And the way these trees work, they're wonderful to get lost in, is that the oldest life form as we know it starts in the center and moves out, migrates out. So we think the oldest life on Earth was probably some sort of archaea, which is a single-celled organism that lived in warm water. And we humans are somewhere over between fungi and metazoa, over in this area by the worms. Anyway, and by the very outer edge of the circle. Moving beyond Earth, NASA's missions have focused on looking for life elsewhere. But we find it's hard to build an instrument that will give you an absolute detection of life. So NASA sent the Viking missions in the 70s to Mars. They landed, they tested the soil and looking for amino acids and some other life, or another test of life, and they didn't find life. And so that actually put a little damper on the search for life beyond Earth. And for many years, and for all of the other rovers and landers that have gone to Mars, there has been no life detection. Instead, there has been this question of characterizing the environment and looking for habitability. So the Curiosity rover, which last month celebrated 8 Earth years rather, or 4 years on 4 years on Mars, has been looking for habitability and on Mars. And actually early in the mission, it was a very successful mission, or it is still ongoing, because they sent on this mission an instrument that can actually determine through X-ray patterns the minerals on Mars for the first time. So instead of saying, oh, let's touch the surface of rock, they actually brought rock on board and drilled with drillings. And you can see in this picture here, these are different colors of some of the 27 drill holes that Curiosity has penetrated up to 5 centimeters, so not very deep, on Mars. And the different colors actually reflect the different oxidation states of the powders that were put on board the rover. And also the different, from these powders, we can infer the mineralogy, or we actually can determine absolutely and quantitatively actually the mineralogy. And from that, we can calculate the waters or the fluids that were present when these rocks were made. And one of the most exciting discoveries of this mission was that the waters at John Klein, Cumberland, the top two, and others, that would have been present when these clays and other minerals were laid down, is actually water that we could drink today. So this is very exciting. So Mars was habitable at one point, as we know it, as we know to be life, and we actually could have been drinking the water. And well, unless there were microbes there that would kill us, it would have been very tasty. So the next mission to Mars, it's on the way right now with Percy, is the same size as this rover Curiosity, size of a car, small car like a Cooper. And it actually has a life detection instruments on for the first time since the 70s. That's very exciting. Once again, the best indication of life would be if something walked in front of us or walked in front of the camera. And these instruments are things like a fluorescence spectrometer and a Raman spectrometer that actually are better apt to characterize the signatures of life rather than actual extant life itself. But still, it's very exciting, and it will arrive sometime next year. Okay, finally, I'm going to give an example of work I'm doing. Last week, in between firestorms, I was able to go with a small group to Lava Beds National Monument in Northern California, where we're beginning our 4th year of an analog mission. So because the planetary missions are few and far between, NASA also supports analog missions to places on Earth that could help NASA and other agencies prepare for looking for life on other planets. Anyway, so this is a project that I lead currently. It's called the BRAILLE project. And we've spent several years with a science team crawling into caves taking samples and trying to characterize the microbial life that lives in these caves and the mineral signatures that life deposits. We don't expect on Mars that we'll find microbial life. Now, wouldn't that be wonderful? But we do think that there's a good sign that if there is life or was life on Mars, we could find a record of it in the geochemistry of the rocks. So here you see the Spot robot just walking autonomously in Valentine Cave, one of the caves at lava beds. And it's very exciting. I don't get to drive Spot or direct Spot, but I do talk with the robotic engineers who do. Anyway, and here on the left you see, or the bottom rather, you see 4 examples with a little alien for scale of 1 inch. 2.5 centimeters. You see some of the mineral features we see, whether the little cave corals, little polyps, little coralloids that drip down from the surface of the caves, or actually mineral crusts that are formed with fractal patterns by microbes interacting with water and rock. And these are features that could persist. These are all also predominantly silica. So I call them cave corals, but they're not carbonates, they're mostly silica. And they could persist over geologic time, and so I'm very, very excited about the potential. Having said that, NASA or other agencies have no planned trip to Martian cave. We have seen over 1,200 tentative caves on Mars, and we are pushing for this, but things take time, and so I hope in my lifetime at least, we will have our first mission to a Martian cave. So I'm going to wrap up now, but I wanted to say that, finally, what makes a habitable planet? Well, we have the best example, of course, in our solar system, us, but we're also looking for life other places in the solar system and also elsewhere. So look for life beyond Earth. And to do that, we look for exoplanets or life beyond Earth, and also how do we detect them? Well, we think about things that live in the Goldilocks zone, that is a place where water could be present on the surface on a planet. We look for rocky planets, and we now are starting to look for atmospheric signatures that could indicate life. Now, having said that, in our solar system, we've discovered in the past 20 or so years that actually a lot of the outer moons have liquid oceans below the surface, like Europa, Enceladus, others. We even found a body in our asteroid belt that seems to have a liquid ocean or ocean body or water body under the surface. So maybe the Goldilocks zone could be broader than we think about it now. And it's helping us to redefine our criteria and environments to search for life beyond Earth or beyond our solar system. So here's another example of this with the TRAPPIST zone that astronomers discovered, where there's seven planets of rocky nature, and 3 of these are in a Goldilocks zone. But based on what I just mentioned, maybe all of them could harbor liquid ocean. So it's very exciting. Fortunately, right now, it would take us many years to get there. But that's why we're developing more and more stronger remote tools. And with the James Webb telescope coming online in 2 years, it'll be an exciting way to increase our detection of over 8,000 exoplanets. Right now, I actually have an app on my phone that lets me know whenever there are new exoplanets logged into the database. It's fun. Anyway, now just a segue to Gerhard. I'm just going to say, where do we come from and where are we alone? These are driving questions in astrobiology, but we're answering these at the very sort of baby step level, fundamentally. But ultimately, what drives us all is to know, to think about answers to these questions and think about possibly life that could be intelligent elsewhere in the solar system and beyond. So as Carl Sagan said, we are made of star stuff. So in the past 20 years, the Sloan Digital Sky Survey and others have looked into the center of the Milky Way galaxy and detected all of the building blocks of life. The 6 primary ones: hydrogen, carbon, nitrogen, oxygen, sulfur, and phosphorus, and seen all these elements everywhere. And then the metal elements that we also need for growth and sustenance. So it makes sense that we might find life somewhere else, or rather it's quite pretentious to think we're the only life in the universe. This was characterized, that the likelihood of finding intelligent life was characterized or captured by Frank Drake, who wrote this equation, the famous Drake equation, on a napkin in 1961, where he describes N, the number of communicating civilizations in the universe, i.e. those with generating electromagnetic signals that we could detect from Earth, and based on all these elements to put into that equation. I won't go through them right now, but I guess you'll get a copy of the slides. And it's just an interesting way to try to frame this question of, are we alone, and how many other civilizations could be out there. And finally, I mentioned ETI, extraterrestrial intelligence, SETI, the search for extraterrestrial intelligence, and METI, the message for extraterrestrial intelligence. And these are, I guess, all very exciting areas and are open to the world to think about. And this is a picture of the Very Large Array in Socorro, New Mexico, that's been listening to only a tiny fraction of the sky for decades. And with that, I guess I'll end here. And I hope this is a nice segue to you, Gerhard, to talk about astrosociology. And hand it back to you, Alyssa.
Thank you very much for this excellent presentation. I've seen a ton of questions, but first let's go into the presentation from Dr. Sonnert on astrosociology, and then we'll address all of those during our live Q&A. So Dr. Gerhard Sonnert is a lecturer in astronomy at Harvard University and a research associate at the Harvard College Observatory. He has been teaching a course on astrosociology since 2017. His research interests include gender in science, science education, the sociology and history of science, and migration. Among his books are Gender Differences in Science Careers, Who Succeeds in Science, the Gender Dimension, Einstein and Culture, Ivory Bridges Connecting Science and Society, and What Happened to the Children Who Fled Nazi Persecution. He holds a master's degree and doctorate's degree in sociology from the University of Erlangen in Germany, and a master's degree in public administration from Harvard University. So Gerhard, after hearing all about what astrobiology is and the search for life in the universe, what is astrosociology? If you're still with us. I just realized that he's not. Okay, this is a good thing. Hopefully he'll be able to reconnect. And I think while we look for life, which is looking for Gerhard, we should move to address all the questions that Jen was having during during your presentation, which is, why are there stromatolites, and I apologize for the pronunciation, of west coast of Australia? Why are there primitive systems still active?
Why are there stromatolites in Western Australia? And why are they still active? Actually, that's a great question. Stromatolites are one of the oldest life forms we know, and they're mounds of layers of different microbes that are also help precipitating a rock. So you essentially end up getting these really cool little bumps, and they persist. This is our oldest known record of life morphology, and I think it's just a very adaptable system. And these are carbonate. They leave behind a carbonate record that then has been replaced by silica in rocks of the Pilbara and elsewhere. But these are our oldest dated rocks on Earth. Why have they persisted? Well, I think they've been able to adapt through the changing Earth over the billions of years. How? Well, we're still studying that, actually. People have samples of living stromatolites in Shark Bay, for example, in Western Australia, and also in Baja California and many other places around the globe. And this is a good question. We want to know how this life can be so adaptable and persist over billions of years.
Well, thank you for that detailed answer. I think it connects to our next one, which are, which chemical compounds, building blocks, can best describe life? And I think you talked about it in your presentation, but if you could address it. Do you have the special formula?
That's the billion-dollar question. Well, we look for amino acids, and initially that was, that's building blocks of life, but we do find many ways to make amino acids without life, so abiotically. So now we think, well, gosh, RNA could be a good sort of detector, rather, or perhaps a lipid, which is makes up the cell walls. So these are that's a very good question, and in fact, in our in astrobiology, we are still deliberating about what criteria will give you an unquestionable signature for life. So I think, of course, the genetic material would be, but that's a pretty large organic molecule that's sensitive to decay over time. So we're thinking, now more the thought is, what sort of smaller lipid patterns or smaller molecules could be an indication of life.
Thank you. Well, I think we have a third question, which is what impact does different levels of radiation temperature have on biological system? As they found bacteria on the Titanic wreck, will they find bacteria on the Mars rovers eventually?
Oh, that's also a good question. So how does radiation affect life? Well, you may have heard that we found microbes that form spores and have been living on the International Space Station for some years now. So normally we think of radiation as detrimental to life, i.e., it kills us, right? And we're protected on Earth with the magnetosphere, which is great. But we think that one of the challenges to life is a radiation that breaks down the DNA and makes you not able to reproduce or thrive. And we think on Mars that doesn't have a strong magnetosphere, that radiation penetrates. Models suggest that radiation would essentially sterilize life up to about 3 meters. That's sort of a ballpark area based on models, but it's hard to know. So some life, like the special form of B subtilis, has been able to persist when exposed to the solar wind and solar radiation, and it could be that kind of life form that could have actually persisted in this notion of panspermia, seeding life from, say, Earth or coming from Earth elsewhere in the solar system. And I don't think I've quite answered your question, but because it's a pretty detailed question, but I hope that's given you a few things to think about.
Well, it is detailed enough considering the complexity of the formula for life, right?
Yes,
So,
I see Gerhard's back.
yes, I see it too. This is fantastic. Gerard, can you hear us?
We can say that if there is water, that means there is life, correct?
Ah, no, but that you bring up a very good point. What are the essential ingredients for life? Well, we think life as we know it, we think water. We think the source of organic compounds and some trace metals that support life on Earth as we know it. And finally, a source of energy or an energy gradient to be able to fuel that life. So all of our search for life beyond Earth is guided by our terrestrial bias.
Great. Well, thank you so much, Jen, and thank you for improvising the Q&A right in the middle. I very much appreciate it, and I'm very happy we found life. We found Gerard. He's back and reconnected. Gerard, you're muted currently. Perfect. Are you ready to share your screen?
I'd like to apologize. My whole system crashed, and
Aliens, they're stopping you from talking. They don't want us to know the truth. Oh, he heard me. So he's disconnecting, reconnecting. And in the meantime, we actually had more questions for Jen. So we're just asking you too many things, Jen. We have from Stefan, do you think that some of the extremophiles which live in very hostile conditions around undersea volcanic vents might be used for terraforming other worlds, such as Mars?
Oh, I love questions like this because, you could answer this probably also. We don't know the answer. The thing about the hydrothermal vents is that they're underwater. So we have detected, actually recently we've detected layers of water in Mars, but it's probably ice. So maybe not the same organisms there, but terraforming is certainly interesting concept. And we want to look for microorganisms that could produce oxygen rapidly and thrive in hostile environments. So I think perhaps not underwater, but organisms that could thrive in hostile environments as they're working to terraform the planet.
Interesting. Gerard, I see you connected again. Can you hear us? You're currently muted.
yes, I can hear you.
Wonderful. Well, your presentation is up. Just let me know where to move the slides and I'll move them.
Okay, let me just say something about astrosociology, what it is, because it's not something that's widespread. I think actually the course that I teach at Harvard is one of the few courses on astrosociology. And if you move forward one slide, there's a very broad definition of astrosociology. Yeah, okay. It's the study of the interrelationship of space-related phenomena and human society. So this is a very kind of catch-all definition. In sociology and I guess in social science in general, we like to distinguish beliefs and behaviors, things that are in people's minds and things that people do. And astrosociology relates to both of these. It's beliefs and attitudes about space. And interestingly, most of our ancestors didn't think of space as space. They would call it sky or maybe heaven. And only we now talk about space. And so we in astrosociology talk about the development of these beliefs about space. Um, we talk about behaviors and activities that relate to space. The questions are who is doing it? Who is actually involved in the space endeavor? Why are they doing it? And what are the results of these activities and behaviors? And one of the big sociological insights is that there are often unintended consequences of activities in action. People do things for one reason, but then something could happen that nobody anticipated. And that's also something that's very important for astrosociology. If you could move it up one slide, please. Okay, this is astrosociology in the classroom. I have taught astrosociology in the astronomy department since 2017. This is also a summer course, basically condensed by half. So it's half the time the same content, and it just takes a lot of hours in the week. And please advance one more. What are my main goals in teaching astrosociology? Why do I do that? And I want to emphasize that space exploration is not only a scientific and technological enterprise, but there are social dimensions to it that I just mentioned, and forgetting about those or not thinking about that is perilous. Unfortunately, there's a pattern in human history that humans tend to do things that are technically possible and not wonder about what might be the fallout of it till it's too late, and then it happens, and then uh, people have to mop up these unintended consequences. And I hope that in astrosociology, the students will get a better idea of the consequences on the social level, and might be able to predict them and maybe even work toward avoiding some of the consequences that might be bad. So for anyone who goes into the field of space exploration, of astronomy, and so on, I think thinking about sociological aspects might be important. But there is a second goal that I have, and Alyssa just brought it up, and that goal is for students who don't even want to be professionally involved in astronomy or space exploration, who want to do something else. And also when, of course, when aliens come, astrosociologists will be very popular, but that's not a career prospect that people should work on. Like, I become an astrosociologist, so I'll go on all the TV shows once the alien comes. That's not a solid plan. But for those students who go anywhere else, they might. Could you
Oh,
just go
sorry.
back?
Here we go.
I'm not. For those students who are not professional space scientists, I think the advantage of studying astrosociology is developing a habit of mind for dealing with something extremely strange, because we can probably not think of something more strange than alien civilizations, aliens, and that kind of thing. And I think um, the dealing with these problems that are so way out of human routine help you think about various other strange things that you might encounter in life that are not related to aliens, but it provides you a certain apparatus of thinking about it. Now please advance, uh, Alyssa. So I've talked about the goals, and for the rest of the talk, I talk about the topics that I put up in order to achieve that goal. And then at the end about the pedagogy, and the pedagogy, I'll go on very, I'll almost skip that. That's not that important here. So the first topic is the history and the dual function of astronomy. Astronomy is probably the oldest intellectual activity of humanity. Since I always take about 200,000 years of humanity, but this is people have looked at the sky and thought about the sky from the beginning. And the dual function is that astronomy at the same time was extremely practical. It helped in timekeeping, in figuring out the seasons of the year, in navigation, in telling position. So it's a very practical thing to look into space, into the sky. At the same time, it was very sacred. A lot of religions place their gods somewhere in the heavens too. So it was always this dual function. Very interesting from an sociological point of view. Then we talk, in the course, we talk about science fiction, because there again you have an interplay between society and technology and space exploration. Often space explorers, when you read their biographies, say they were inspired by science fiction. On the other hand, science fiction authors are inspired by what goes on in space. And sometimes human problems that we have in society right now get projected into space as almost a thought experiment to think about these things in a creative way. We'll talk a little bit about truth theories. That's because space is pervaded by conspiracy theories, UFOs, and all sorts of things. And the students should learn about distinguishing science and pseudoscience and how to think about UFOs and that sort of thing. Then we come to something that Alyssa is very familiar with, cosmic threats. What happens when an asteroid is on collision course with Earth? We talk about space exploration, the moon, Mars, asteroids, asteroid mining, that kind of thing. And then finally, we get into the alien topics, like, does extraterrestrial life and civilizations, do they exist? I mean, that connects to Jen's talk. And if you go on, Alyssa, please. SETI, METI. SETI means listening for signals from outer space. METI means active SETI. It means actually messaging, sending out messages to aliens. And people wonder, is this a good idea? Should we actually compromise our cosmic position or not? So there's a debate about that. And then, of course, the sociological implications of contact, which would be tremendous. And yeah, so finally, and I'll try to bring this to a close quickly. How do I teach this? And the students in my class have to do a lot of active work. It's almost the opposite of a lecture course, because students have to do class exercises. They have to do simulations like the one that Alyssa does. They have to work in groups and teams. We do readings of important texts. We do whole group discussions, formal debates. One of the formal debates is, of course, how likely is it that alien civilizations exist? And on the one side, you have the position, the cosmos teems with intelligent life. There are alien civilizations all over the place. And on the other hand, the position is we are alone. We are the only ones. And people fall somewhere in the middle of that. Hands-on work is always, that's fun. We build quadrants and make sun measurements in honor of our ancestors. who didn't have GPS and smartphones and had to figure out a lot of things by measuring the position of the sun. So we do that, and the students built those simple instruments with a protractor string and the weight. So it's very easy to build, and it gives them some appreciation of what our ancestors did in terms of measuring the sun and the stars. And we do field trips and have guest lectures, and there we are really blessed in the terms of the environment we have in Cambridge and at Harvard, because there's a lot of people there who do interesting stuff. So, and I wanted to conclude now, because I apologize again for holding you all up. That might.
Yes, thank you so much, Gerald, and thank you for reconnecting. And I know it's always a struggle, you know, with Zoom when you're disconnected, when everything crashes. It happened to me in the middle of class, so I understand your pain, and I very much appreciate the fact that you reconnected. And we can see you, so that's fantastic. I have just a quick question for the two of you, and then we'll get into the formal Q&A with the audience. So, how do you see astrosociology and astrobiology connect?
I think there are different ways of looking at it. One of them is that astrobiology deals with the origins of life and very simple life. And that's what Jen referred to with the NASA decision to stay away from SETI. And astrosociology, of course, mainly deals with life that's advanced, that's civilized, that has a technology. So that's one simple distinction between biology and astrosociology. Another thing, astrobiology itself is, of course, a subject of astrosociology, because we study who does astrobiology, why do people do astrobiology, what will come out of astrobiology. So we study, as astrosociologists, we study the astrobiologists. By the way, we also study ourselves, of course, because we have to ask ourselves, why do we do astrosociology? And the final aspect that I want to bring up is about a key concept of, I think, astrobiology, which is evolution. Evolution is such an important concept in biology, and it's almost synonymous with the evolution of life. Like that's how I think biologists look at evolution. Astrosociologists would take a wider view on evolution, and we would probably say that biological evolution is maybe one way of evolution to happen, biological life, but evolution could be much more general, and evolution could probably happen not for biological life but for artificial life. And so we might be at the cusp where we say, okay, biological evolution was fine, but now something else is taking over, and then people, I mean, that's where the science fiction aspect comes in. People talk about robots, people talk about artificial intelligence, and basically some kind of a self-guided evolution, which in biology doesn't happen so much. I'm not a biologist, but I seem to understand that mutations are not directed, they just happen, and then it turns out whether they're good or bad, and there might be some other flavor of evolution. So that's my last point about how astrosociology and astrobiology are connected.
How about you, Jen?
Gerhard, I like that response, and thank you. It's very interesting thinking about this coevolution, and but I also like your phrase, developing habit of mind. So one thing I like about colleagues who study astrobiology is this, just forcing yourself to be uncomfortable and be open-minded and think about things we don't understand and things that are poorly constrained. So I think that's a lifelong growing experience, which can be painful. But no, it's very interesting thinking about coevolution. You're absolutely right. And when Jim Lovelock proposed the Gaia hypothesis in the 1960s, it was because a lot of scientists were skeptic about this, right? But more recently, as I mentioned, we've looked at sort of the complexity of mineral forms, so from the rock record, and how that complexity is developed over the billions of years on Earth history. So I think you bring up a really interesting point of this sort of coevolution of rocks and life, and this codependence of the ingredients. So in other words, does life is complex? Does complexity require life? Does life create complexity? And then, ultimately moving on toward artificial intelligence. I mean, we can all download or go online and play with machine learning algorithms, and then let the machines take over and do that beyond, right? And we're actually training this robot to look for, using a training set developed by people to look for evidence of life in these caves autonomously. And, at some point, well beyond my understanding, at some point the algorithms become more sophisticated than we can even imagine or keep up with. So that'll be interesting to see how evolution happens beyond people. What's the next step?
Well, thank you, Jen. And I know we're getting close to the end of the hour, but because of the technical difficulties, I thought we could maybe stay maybe 5 to 10 more minutes with our audience. I had one final question before we open up the floor for questions again. And first of all, thank you, Jen, because I saw you very active answering question in the chat. So it's working well. And Gerhard, in the chat, participants were asking descriptions about your astrosociology course. So I linked the Zoom link, the web link to your course in the chat, so feel free to check that out as well.
Thank you very much. That's
And both the presentations will be shared with our audience and through SpaceConneX and the Space for Women show. So the last question that I personally had was, I've been thinking of, this plate that we sent out with this man and this woman, and the man was saying hello. And I have a question for both of you, because Jen, you're a UNUSA Space for Women Network mentor. And Gerhard, you spent a lot of your career researching the role of women in STEM and the place of women in STEM. So are we expecting for the next plate to be sent out to have the woman saying hello?
Gerhard, I'll let you answer, but I'll preface by saying I don't know of plans for the next record.
There was also this big debate about moral turpitude because they were naked. From a sociological point of view, this is very interesting because how do you communicate to aliens? Do you communicate like a biological fact of what humans look like? And how does that square with the social fact that it's considered immoral or not appropriate to show a naked human body like that? And there are all sorts of problems with that Voyager picture and the Voyager disk. And one of the students in the Astrosociology class actually wrote his final project on the music selection that they sent out. The question was, what were they thinking? Were they thinking that the aliens would really appreciate human music, and why did they select these various things? So yes, it would be very different. But in terms of women in the space, I work in the science education department at the Center for Astrophysics, and we do large surveys of young people, freshman undergraduates, and we ask them about what do they value in their future careers. And they get a questionnaire, and they get, say, from not important at all to very or extremely important. And we ask about things like money. Money important. It's important to some extent for everyone, but is it extremely important? Not so much important. Is fame and becoming famous important for you? Not at all. Yeah, it is. Is having some free time to spend outside of your job important for you? Yes or no? And so the young women and men are surprisingly similar now. But there is one difference that we find repeatedly, and that other colleagues have found too. And it's on the questions: how important is it to you to work with other people? Huge gender difference. Women are more interested in working with other people than men. and how important is it to make a difference for society in your job. Women are much more interested in doing that. For the men, the other things are more important. So we have the stable difference that hasn't moved for the last 10 years, and I think that that can be connected to what you're doing, Alyssa, and what you're doing here, and looking at space exploration from a more humanistic or human point of view, and considering the uh, ramifications. I guess looking at the group here, there's also a lot of females and women in it, and so there is this divide of engineering and building stuff and building rockets and shooting now and thinking about what it all means, and females are more predestined to doing the second thing, and I think that's a draw that you can use if you want to have a kind of a gender equity in space exploration, because the human ramifications of it are very obvious, and so that's how you can attract women into the field.
Women in space system engineering, building the rockets and making everybody work with each other. I love it, and I agree.
No, I just want to comment, that's so interesting, Gerhard, that you summarize those sort of distinctions between sort of the man's approach and woman's approach to work, and expectations and aspirations for work. In terms of the golden record and the METI, or the message, what an exciting time it must have been in the 70s to craft that message. And there was a very small group of people, mostly men, who determined that message. And I can see today how having this could even, the hello from the man could be construed as, violent, for example. And the woman was much more demure. But I don't know if the message would change. And just, I assume everybody knows what the golden record is, but it was a metal was placed on Voyager 1 and Voyager 2 as they were launched to fly by a lot of the bodies in our outer solar system, and now they've moved past the last body in our solar system. And I thought it was that it would have etchings that would equate to the story of humanity and what we value. And so naked pictures or outlines of us with not too much detail, because they were line drawings, and then the music, and then history of humanity on Earth, and things about our planet. So I know there are people whose job is, or they spent their obsession or passion is to craft the next METI, or message for extraterrestrial intelligence. And thinking of Doug Vakovich in particular, who left actually SETI and founded his own company called METI. And I mean, what a challenge. And then there are others, of course, who are think, well, who are you to determine the message for humanity? And that's true. I mean, how this message was very biased by white men from NASA, or from with NASA affiliation. How would that message elicit change as we think about diversity on the planet? And it would, actually, that would be, Gerhard, that would be such an interesting full course to look at just the golden record, and how how we as individuals and as teams come to some consensus as to the message we send out to the universe. I think it's a question for a long debate, and would be wonderful to have participation from many, so if not all.
Absolutely. Just one another aspect that I just came to my mind. The best technology for playing the golden record in those days was a record player, and the young people in the audience might not even really know what that is, because now we have CDs and thumb drives, and everything is on the cloud anyhow. But these were discs that had like grooves in them, and they were turning, and that's how the sound was transmitted. And that was, in those days, that was cutting edge. And right now, it's already a kind of an archaeological artifact, and that's just one of the challenges for contacting extraterrestrial civilizations, if they exist. Technology changes so quickly, and what we think is cutting edge might just be a fleeting phase. Even like the sending out electromagnetic signals that we think is the only way to go, that might be a fleeting intermediate phase for a civilization where they think, yes, that's what we do, but 100 years from now we have a different way. It's like smoke signals that for the Chinese and the Great Wall, this was the technology, but it stopped, and the aliens will not see smoke signals because they are advanced and they work on other channels. So that's just my my idea that I had when Jen talked about the golden record. It's just technology is moving so fast.
Well, and one of the questions, yeah, that's a really good point. And one of the questions in the chat had to do with how would we communicate with an extraterrestrial intelligence? And for that, of course, I go back to science fiction, where great minds have addressed this. And we often see the use of mathematics, or use of patterns, or use of pictures. Yeah. So Stephen, you're talking, but you're muted. But I see your enthusiasm. That's great. That's another really cool question for a debate. Oh, hi, Ariane. You're saying goodbye. Okay. Anyway, Gerhard, I want to take your course. There's so many topics that you've raised that come up. It's cool.
We're close to wrapping up. I just wanted to say, for those who are interested in talking about the evolution of those objects, I would refer to you also to the fantastic episode 12 of the series, where we talked with Alice Gorman about space archaeology. So space archaeology and the objects that are in space, and all those documents that we send, and what comes out of what we create in space. I will end the questions from the audience with a comment from Janine, which I thought was very on point considering this COVID situation and social distancing, where she said, well, would touch be the best way to communicate? Because sight and sound might not be part of that other sense system, but physicality through touch seems most likely, don't you think? Well, if they do not have COVID, I don't see a problem with that, but now, if you have any final thoughts, concluding thoughts, Gerhard and Jen, I'll let the floor to you. Then we'll do our usual group picture, and we will say goodbye to all of you.
First, I will just say thanks, everyone, for joining this show on your weekend time. I always like talking about astrobiology and also learning about other approaches to astro science or science fiction. And so it's a pleasure to see the interest here, and also I think I love that astrobiology inspires your imagination, and it's open to everybody. And there is always an element of astrobiology that can fit into your life, whether as a hobby or as a profession. And I think by going back to Gerhard's quote about developing that open mind. It's a way to keep communication open and keep our eyes open for possibilities and inspiration in our world and beyond. So thank you.
Thank you, Jen. Gerhard, any final thoughts?
Yeah, maybe I'll leave the audience with a puzzle about astrobiology. Let's assume that astrobiology finds that primitive life is really abundant in the cosmos. They find it on Mars, they find it on the moon, they find it on asteroids, they find it on Jupiter moons, and so on. So it's really something that happens a lot. What does that mean for the probability of intelligent life existing? So think about it. It's called the Great Filter Theory, and it's not as easy as you might think immediately. So there are different answers to it. That's what I want to leave you with, is if primitive life is abundant, the ones that biologists find, what does that mean for the probability of technological civilizations?
How do we contact you when we come up with the answer to the puzzle?
Yes, yes, Gerard. We
Well,
have several people in the chat. If you could both put your email addresses, I think they would be more than happy to reach out.
yeah, but there's no real good answer. I mean, that's one of those conundrums that I just want you to think in the spirit of astrosociology. That's a typical astrosociological question we would ask. We don't know the answer. We just want to train our mind to think about difficult and weird problems.
Very nice. Well, now I'll put everybody on gallery view and we'll do if you can turn on your cameras for those who are still around here. Our usual sign to say goodbye is the little Star Trek. So I welcome all audience member to turn on their camera and give us a big smile. Great. Thank you so much to all of you for joining us. And we will come next week with another fantastic Space for Women show. Thank you to Dr. Jen Blank and to Dr. Gerard Sonnert for being there with us and telling us all about astrobiology and astrosociology.
Thanks for having us.
Thank you.
Have a wonderful weekend, everyone. See you soon.
Bye-bye.